Welcome to The Explainer. Today, we are treating your Cambridge 9618 computer science exam exactly like a high-stakes space mission. Now think about it. In a real rocket launch, there's absolutely zero margin for error. Every single calculation, every boundary condition, every single line of code must be meticulously planned and perfectly executed for that launch to be successful. You can't just guess your way to orbit. And in the 9618 syllabus, building upon the foundational knowledge you might have gathered from the 0417, 0478, 0983, 0984, or 2210 syllabuses, the critical thruster that propels you from a solid B grade all the way up to an A star is your total mastery of composite user-defined types. Specifically, we're talking about records. Now, to really understand the challenge here, I want you to picture two different computer science students. We'll call them Alex and Sam. We see these two profiles all the time in past paper responses, like in the notoriously tricky 9713 papers. Alex is the overloader. Alex memorizes every single raw computer science fact from the textbook and just dumps it onto the page. No analysis, no context, just a wall of theory. Then you have Sam. Sam is the rusher. Sam sees the question, panics about the time, rushes through the code, and completely misses the specific command word requirements the examiner actually asked for. When you put their flawed answers side by side, it's just a sea of red pen marks. Alex loses marks for lack of application, and Sam loses marks for ignoring the prompt. If you've ever felt like Alex or Sam, or if you're just wondering what the principal examiners are secretly looking for when they grade your papers, you are in the exact right place. We are going to completely deconstruct how to approach these questions so you can launch your grades into the stratosphere. To make sure our mission is a total success, here is our expert's roadmap for today's session. First, we'll establish the core principles of records. Second, we'll break down the technical methodology. And finally, we'll dive deep into examiner insights and evaluation. Let's get moving. Okay, let's dive right into this first section, the core principles of records and building out your conceptual framework. So, what actually is a composite user-defined type? A record isn't just a random collection of variables that you throw together because you feel like it. Actually, scratch that. It's more like a highly structured conceptual framework requiring systematic analysis and evidence-based reasoning. In simpler terms, a record allows you to group different data types together under one single logical identifier. Imagine you were trying to monitor a spaceship's telemetry. You're going to have a string for the astronaut's name, right? You'll have an integer for their heart rate, and maybe a Boolean value, true or false, for whether their oxygen suit is properly sealed. A record ties all of that disconnected data into one unified, pristine package. Now, remember Alex, our student who just dumps textbook facts? Alex would write, "A record is a data structure that holds multiple data types." Boom, done. And Alex would get barely any marks. The source material emphasizes that top-tier students don't just memorize the syntax for this stuff. They exhibit a deeply connected conceptual understanding of exactly why and how we group data this way for a specific problem. They use frameworks like PEEL, point, evidence, explanation, link, to structure their thoughts, which we are going to break down for you very shortly. And this brings us to a massively critical realization. Cambridge computer science demands so much more than rote memorization. You literally cannot just memorize a textbook definition of a record and expect to get an A star. Your knowledge must be completely 100% transferable to unfamiliar contexts. The exam isn't going to ask you to define a student record for a school database system like every single textbook does. It's too easy. They might ask you to design a record structure for a robotic warehouse system sorting hazardous materials, or a deep-sea submarine sensor network measuring pressure and temperature. You have to take the pure theory you learned and adapt it on the fly to a completely new, totally unfamiliar scenario. This is where Sam usually fails. Sam rushes in, sees the word record, and just writes out the code for a school database because that's what was practiced at home, completely ignoring the robotic warehouse context the command word demanded. Which leads us to this crucial question. Why do students find applying concepts to unfamiliar contexts so incredibly hard? It's the #1 roadblock to achieving that A star. It usually happens because a student has memorized what a concept is, but hasn't practiced how to dismantle a brand new problem to see where that concept actually fits. They freeze up entirely when the scenario doesn't exactly match their past practice papers. But don't worry, because we're going to reveal the exact algorithmic solution to this problem right now. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's get into the strategy that fixes this. Section 2, the technical methodology and executing the method mark strategy. This is where the magic happens. Here is a fascinating concept that most students totally overlook, the method mark strategy. Examiners actually award marks for the process itself, not just the final correct answer. I mean, this should instantly reduce your exam anxiety. If you apply a highly structured, systematic approach to your problem solving, you can sweep up tons of method marks along the way. Even if your final code has a minor syntax error, maybe you missed a semicolon or used the wrong bracket, showing the examiner your logic and your process proves you understand the algorithmic thinking that is required. This is where you need to master your command words. When a question says evaluate, it doesn't mean describe. It means you need to look at both sides and make a judgment. When it says identify, it means pull a specific fact from the scenario. And this is exactly where that Peel framework overlay comes in perfectly. Point, evidence, explanation, link. Make your point about the data structure, give evidence from the prompt, like mentioning the specific submarine sensor, provide an explanation of why a record works best here, and link it back to the command word. Our rushing student, Sam, loses all these method marks because there is no Peel structure. Sam just writes the code, gets the logic slightly wrong, and scores a 0. But if Sam had used Peel and showed the working out, the examiner could have awarded 3 out of 5 marks just for the logical process. So let's walk through this algorithmic thinking progression step by step to build what I call the computer science success blueprint. Think of this as the ultimate transformation for your answers. First, step-by-step decomposition. You take the massive, scary problem and you break it down into tiny, manageable functions. Second, appropriate data structure selection. This is the exact moment where you look at the problem and decide, I have multiple related variables of completely different types here. I absolutely need a record. Third, efficient code implementation, writing clean, highly logical code to declare and manipulate that record. And fourth, rigorous testing, thinking about how to prove your solution actually works under pressure. If we put Alex and Sam through a 60-second rewrite attempt using this exact blueprint, the transformation is incredible. Those red pen marks suddenly turn into green check marks. Alex stops dumping random facts and instead decomposes the specific problem. Sam stops rushing, selects the appropriate data structure, and writes efficient code that actually answers the prompt. If you display this exact 4-step progression in your exam answer, you are actively building a robust, maximum scoring response. Let's dig a little deeper into the procedural framework required when you are handling data within these records. You absolutely need critical data interpretation skills. It's not just about setting up the structure. You must be able to extract data, sometimes even from raw binary representations. You have to perform accurate calculations on that data, and most importantly, you have to draw evidence-based conclusions. You aren't just moving numbers around a screen, you are proving to the examiner that you understand what the data actually means within the specific context of the question. If the astronaut's heart rate integer spikes above 150, your code shouldn't just store that number. Your logic needs to recognize it as an anomaly based on the scenario. Every calculation you perform must be supported by the fundamental logic of the scenario provided. This is exactly why those changes to Alex and Sam's answers add so many marks. They move from abstract coding to practical evidence-based problem solving. That brings us to our final and, quite frankly, most critical section: examiner insights and heeding the red flags. You really want to pay attention here. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's look at exactly what the people grading your papers want to see. Examiners want to see a very specific problem-solving framework when they grade your algorithmic applications. They call it the Deconstruct, Solve, Evaluate framework. First, identify the given information. Literally highlight it right there on the paper with your pen. Second, break it into logical steps. Third, solve it systematically using the blueprint we just discussed. Fourth, check for reasonableness. This is huge. Does a spaceship velocity of -5,000 make sense in this context? Probably not. You need to catch that. Finally, make justified recommendations based on your findings. If you structure your long-form analytical answers using this exact flow, you are handing the principal examiner exactly what they are looking for on a silver platter. It shows maturity in your coding logic. Now we are entering our interactive workshop phase. Let's do challenge number 1, the data scan. I want you to look at the difference here, which brilliantly illustrates a classic trap. We have the generic textbook answer versus the context-linked answer. Imagine you have 60 seconds on the clock to look at a complex data table for a spaceship fleet. A generic answer, like our friend Alex would write, might correctly state that a record is a composite data type holding multiple variables. That is factually true, but it scores incredibly poorly on the actual exam. It extracts no trend from the data. A context-linked answer, however, scans the data and says, a record is required here to store the transport vehicle's unique registration plate as a string, alongside its current orbital speed as an integer, to monitor fleet safety. Do you see the massive difference there? The second answer proves you aren't just a walking textbook. It proves you extracted the core trend from the data source, and you are acting as an active problem solver. Moving to challenge number 2, find the flaw. I'm going to read a quote from the Principal Examiner Reports, and I want you to identify exactly why students lose marks here. The report says, "The classic mistake is providing generic answers not specific to the question context. Always link every point to the given scenario." So, if I show you a sample paragraph that says, "I will use an array of records to store the data because it is efficient," the record will have a string and a Boolean. What is the flaw? The flaw is that it completely lacks context. I want to repeat that examiner warning with heavy emphasis. Always link every point to the given scenario. If the exam question is about a municipal library database, your answer must be absolutely dripping with vocabulary about books, borrowers, late fees, and due dates. If you write a beautiful, syntactically perfect piece of pseudocode but fail to link it to the actual scenario the examiner provided, you are going to hemorrhage marks. Let's move to challenge 3, speed writing. You have 30 seconds in your head to formulate a perfect Peel paragraph. But while you do, you must avoid these top 3 student mistakes that the examiners flag year after year. Number 1, using the wrong formula or algorithm for the context. This goes back to failing to adapt. Don't use a linear search if the data is sorted and the context demands efficiency. Use a binary search. Number 2, forgetting boundary conditions and edge cases. When you create a record array for our spaceship, did you test what happens at index 0? What happens at the absolute maximum size limit of the array? Examiners specifically hunt for these edge cases in your code. And number 3, which we just hammered home, answers lacking context specificity. These 3 traps are the absolute quickest way to plummet from an A star down to a B. If your speed-written paragraph addressed the context, check the boundary, and use the right algorithm, you nailed it. Now we are moving into the final system. Occasionally, the exam will ask you to compare records to another data structure, like 2D arrays. This requires rule number 1, command word decoding. Compare has very strict rules. You must identify both similarities and differences. You can't just list what's the same.